2009, BC number 1. And they've given us a graph here that tells us that she rode a bicycle on a straight road from home to school, starting at time 0, arriving at school in 12 minutes. Time interval 0 to 12, her velocity is given by the graph. And the first part here in part A says find the acceleration of Karen's bicycle at time 7.5 and indicate the units of measure. So we can see that between 7 and 8 there's a negative slope there. So knowing that that's a velocity graph means we need to find the slope between those two. Would give us the answer we're looking for here for part A. So the 2 points in question are 7 and 0.3, and then 8 and 0.2. So she's going from time 7, her velocity is this, time 8, her velocity is this. So the acceleration would be the change in velocity over the change in time. So 0.2 minus 0.3 over 8 minus 7, negative 0.1 on top over 1, negative 0.1. And indicate units of measure. The velocities here at the top, they're measured in miles per minute, and the bottom is measured in minutes, so it would be miles per minute squared. Keeping in mind that any acceleration should be some distance unit over some time unit squared. And ultimately 2 points for that one. One to have the correct answer and one to have the correct units. Questions on part A. Okay, part B. Says using correct units, explain the meaning of 0 to 12 v of t dt. Absolute value of that is. So if we had the absolute value of v of t dt, what would be the meaning of that using correct units? Well, ultimately we know that the absolute value of the velocity, if we integrate that, we're going to get the total distance traveled in miles from time 0 to time 12. Right. So 1 point for recognizing that that is correct, that it's the total distance traveled in miles. And the other part asks us to actually find the value of that. So we know that if we're going from 0 to 12 here, we just need to find the different shapes here are just circles, or not circles, but triangles, rectangles, trapezoids, whatever the case may be. Bottom line is we just need to find the area under that curve. And the 0 to 2 part should have been 0.2. The 2 to 4 was 0.2 also. Okay, keeping in mind it's beneath the x-axis, but we're doing the absolute value, so it gets treated as a positive. And then that last part going from 4 obviously has none, but if we go from 5 to 12 and break that shape up however we do, should have gotten 1.4, so the total will be 1.8 miles. Okay. So another point for figuring out that the area in question there was 1.8. Any questions on how we got any of the number parts? Alright, part C says shortly after she left home, she realized she left her calculus homework at home. She returns to get it. At what time does she turn around and go back home? Give a reason for your answer. Well, we know that that is at time 2, because at time 2 the velocity changes from what? Why do we know it's at time 2 where she turns around? The velocity changes from what? It changes from positive to negative. So velocity changes from positive to negative. And simple as that. So 2 points, one for the time, one for the reason. Questions so far? Alright, then in part D they give us a function for this other person, Larry, who was riding his bike. And it says, who lives closer to school, Karen or Larry? And ultimately, we know that if we're going to do it in 12 minutes for Larry, if we go 0 to 12 of our W of t function, okay, we wind up with 1.6. And keep in mind that we're not going to use absolute value here because we don't want the total distance traveled in case Larry turned around and had to go home too for some reason, right? We want the displacement, so we want to know how far is it from home to school. We know that time 0 he was at home. We know at time 12 he was at school. So the displacement here is what we need. So if you do calculate that correctly, it's a calculator problem, of course. Get 1.6 miles. And if you do Karen's displacement, okay, so we put 1.8, but it's not 1.8. That's her distance traveled. Okay, so what is the actual displacement? Okay, it's right up here, but instead of this being positive, it needs to be treated as what? As negative. Okay. So bottom line is those two are gone, and how far is it from home to school? 1.4. So again, who lives closer to school? Remember the question says, who lives closer to school, Karen or Larry? You would say the answer is what? Gary. Don't say Larry lives farther away. That's, I guess, true, but is that really what they asked? And ultimately, it's 3 points, one for each of these if you found the correct displacements and then the correct analysis. Any questions on any of the 9 points there? All right, well, let's take a look at number 2 then. All right, number 2 should look familiar because this is an AV question also. We got a rate function here for people entering this rock concert, 1380 t squared minus 675 t cubed for time between 0 and 2. Says this is rate is measured in people per hour. So the number of people, or it's the rate at which people are entering this concert. So it says no one is in the auditorium at time 0. When the doors open, the doors close, and the concert begins at time 2. So bottom line here, part A says how many people are in the auditorium when the concert begins. So if we have this as our people per hour and we integrate, we're going to get total people, aren't we? So if we just do our integral of r of t dt, 0 to 2, should get 980 people. So 2 points there, one for the integral and one for the answer. And part B says find the time at which the rate, find the time when the rate at which people enter the auditorium is a maximum. So ultimately we want to know, if this is our rate function, this is our r, we want to know when it's a maximum, so we're going to need to find its what? We're going to find its derivative. So if we do that, it should be 2760 t minus 675 times 3 is 1950. Alright, bottom line here is that if we set that equal to 0 when we solve it, we should get t equals 0 and 1.36296. And remember, time 2 is another possibility here because it's a closed interval, so time 0 to time 2. So with that, we can see when the rate is the most. And again, this is the derivative of the rate. We want to know when the rate is a maximum. So if we do the rate at 0 is 0, so that's probably not the answer. The rate at the other endpoint turns out to be 120. Okay, so if we plug a 2 into our rate function up here, we get 120. And again, very typical candidate test problem because they give us a closed interval. So if we want to find the maximum or the minimum, okay, just use the candidate test. Find all the candidates, the endpoints, stationary points, singular points, and plug them in. And if we get 36296 in here, turns out to be 854.527, and obviously that's the biggest one. So ultimately the question then is find the time when the rate is a maximum, so obviously the time here would be this one. This is our t-value here. So our final answer then would be time 1.36296. All right, and ultimately 3 points for that. 1 for finding the derivative and setting it equal to 0. So finding the other critical point, the 1.36296, was worth a point. And then the answer with justification. Okay. And again, this is ultimately justification candidate test. You could use the first derivative test here too if you use the first derivative test. And you show that on the left of this number it's positive and on the right it's negative. Okay. Would be another justification to show that that's a maximum. Questions so far? All right, and then part C was really hard because it's got a lot of words. Not. All right. Okay. Don't get bogged down in a bunch of words. Just sort it out and do the calculus. You got part C is the total wait time for all the people in the auditorium is found by adding the time each person waits, starting at the time the person enters the auditorium and ending when the concert begins. Okay. It says the function W models the total wait time for all the people who enter the auditorium before time t. And it says the derivative of W is given by the following. So we have this derivative function, and it's equal to 2 minus t times r of t. Okay. So that's our derivative function, if you will. Okay. And our job here is to find find W of 2 minus W of 1, which is ultimately the total wait time for those who enter the auditorium after time 1, so after the first hour. Okay. Alright, so keep in mind that I guess the kind of the giveaway here is that if we need to find W of 2 minus W of 1, okay, wouldn't these W's come from the integral of W prime? If we integrated W prime, in other words, if I wrote that right there, wouldn't the answer to that be W2 minus W1? Because what is the antiderivative of W prime? W. And if we use the fundamental theorem, we'd get W of 2 minus W of 1. Fair enough? Alright, so the question is, can we actually find an answer for this? Well, the answer, of course, is, yeah, certainly. This is just 2 minus t times r of t, and don't we know what r of t is? Isn't that the function that we had up above? Okay. So it's just a definite integral problem, and it's a calculator problem, so if you punch it in your calculator, the answer to that is 387.5 hours. Again, that would be the total wait time for all the people that entered the building after time 1. So again, key issue here is recognizing that if we have this W prime, W2 minus W1 is just the integral of W prime from 1 to 2. That's all that is. And 2 points, one for the integral, one for the answer. Questions on part C? Alright, last part then, part D. So is that on the average, how long does a person wait in the auditorium for the concert to begin? It says consider all people who enter the auditorium after the door opens, the door is open, and use the model for the total wait time that you found in part C. Okay. Ultimately, think about just from a common sense standpoint, if we knew the total wait time for everybody, couldn't we divide that by the number of people and get the average wait time for one individual person? And we know the total wait time is just going to be 0 to 2 of 2 minus t r of t dt. Okay. That right there would give us the total wait time for the first 2 hours instead of the first, or the second hour, if you will, the 1 to 2 time. Okay. So that right there would be w of 2 minus w of 0, which is the total wait time. So we can certainly get an answer for that. And then ultimately, once we got an answer for that, what are we going to divide that by? The total number of people that were in the building, which is what we found in part A, which is how much? It was 980, wasn't it? And if we do that properly, it should be 0.776. And the units here are hours. So it means the average person waits about 45 minutes. And 2 points, one for having the correct integral, and one for having the correct answer. So if you just recognize that the integral part gave us the total wait time, okay, divide that by the total number of people, and we'll get the average value. Okay. And if you want to think about it in a little bit different way too, you could think about, I guess one thing that you want to be careful of here is that if you remember, if you recognize that in the first part, if you got this as total wait time, so this integral here is measured in hours. Okay. And so if you divided that by 1 over 2, okay, if you thought of it as an average value problem, you said, okay, well, time is 0 to 2, so that means the outside needs to be 1/2. But if you did that, this is 2 hours. What would the units be if you multiplied 1 over hours times hours? What would the units be now? Wouldn't be any, would there? Okay. So would it make sense to multiply by 1/2? No. Because ultimately we want the average wait time. Okay. And so ultimately the 980 is our people. And so instead of the 2 hours, we're going to go 980 people. And so if we said that in English, though, we wouldn't say hours per people, it would be hours per person. Okay. And ultimately that means our answer here would be 0.776 hours per person, which makes sense. That would be our average wait time. All right. Anything else on number 2? Okay. Let's check out number 3 then. Okay, we have a set of parametric equations here that give us the position of this diver at any time. And it says that x and y are measured in meters. And it says suppose the diver's shoulders are 11.4 meters above the water when she makes the leap. And they give us, instead of the actual x and y equations, they give us the derivatives. So dx dt is 0.8, and dy dt is 3.6 minus 9.8t. So these two give us our essentially our velocity components at any time. Okay. And so in part A here, it says find the maximum vertical distance from the water surface to the diver's shoulders. And so ultimately, if we want to find that maximum distance, we want to know when the vertical velocity component is equal to 0. Because when the vertical velocity component is equal to 0, okay, that means that our velocity in that direction, okay, would be at a maximum. So if we do that, 3.6 minus 9.8t equals 0, and we solve that, we're going to wind up with 0.36735. So again, keep in mind that we're looking for when is y a maximum. Y would be a maximum when dy dt is equal to 0. So really no different than what we do in a 2-dimensional problem, okay? Or just a regular problem that's y in terms of x. If we wanted to know where the maximum occurs, we would set the derivative equal to 0. Okay? So this time the only thing different is that we have different components. We have an x direction component and we have a y direction component. And so again, if we're looking for heights, we're going to need to be dealing with the y direction components. And so with that said, we can find the time. Now, the question though asks us find the maximum vertical distance from the water surface. Okay, so this is the time when we're at the maximum distance. Okay, but remember she started at 11.4, and we're going to add essentially the displacement. Okay, so remember the displacement here would be from 0 to that 0.36375, 735 that is, of our dy dt function. And you got its calculator problem, and this is going to be essentially our, just like it would be displacement, okay, the integral of the velocity would be the displacement. Okay, this is going to be our vertical displacement only because we're dealing with vertical direction, and that's it. So that's going to be our vertical displacement, and if we calculate that, it should be 12.061 meters. So 12.061 meters. And that whole stuff is worth 3 points. One for setting the derivative equal to 0, the y component derivative. One for writing the integral correctly to get the displacement, so we could figure out the actual distance here from the water surface. And then one for the answer. Got to make sure, of course, we add it to 11.4 because that's where our starting point is in the y direction, or 11.4 above the water. Questions on any of those 3 points? Okay. Part B says find A, the time the diver's shoulders enter the water. Okay, ultimately, if we know that dealing with our 3.6 equals 9.8 t is our dy dt here, we ultimately want to know when y equals 0 here. Agreed? So if we could write an equation for y, then we could certainly solve that for letting it equal to 0. So if we did our antiderivative here, we get 3.6t minus 4.9t squared plus c is equal to y. And what do we know about, do we have means to find c here? When time is 0, our y is 11.4, isn't it? So if I wrote it in standard form there, we'd have that as our quadratic equation. And ultimately, if we want to know when we hit the water, we want to know when y is equal to 0. So if we solve this quadratic equation, we wind up with the value of 1.936 seconds. And 2 points, one for writing the equation correctly, one for calculating the correct answer. Again, being a calculator problem, we should spend absolutely no time trying to do the algebra here. Don't try to factor this or use the quadratic formula. Okay? Just put it in your calculator and find your 0. Okay. So again, 2 points here. One for the equation here for y. Okay. One for the correct time. All right, part C. We're asked here to find the total distance traveled by the diver's shoulders from the time she leaps from the platform to the time she enters the water. And so this is where essentially it becomes our distance traveled. And we know that our distance traveled when we're dealing with parametric equations is going to be from 0 to, in this case, 1.936, because that's the number that we just found a minute ago. And our integrand is going to be the square root of dx dt squared plus dy dt squared dt. So again, the total distance traveled by anything that's on a parametric path is always going to be from a to b of the integral, the integrand being the square root of the derivative squared plus the derivative squared. And so if we punch all that in, it gives us 12.946. One for the integral, one for the answer, and the units here are meters. And finally, part D. They ask us for the angle. We want to know what is the angle between 0 and pi over 2 between the path of the diver and the water at the instant when the diver's shoulders enter the water. So ultimately, with that path that we're given here, we got the diver doing something like this. So we ultimately want to know what's the angle between the path and the diver when we hit the water. Okay. So ultimately, here's what we kind of need to think about mathematically. If we're going to figure out that angle right there between that path, it's not, if it was 90 degrees, be going right straight in, it'd be essentially perfect. Make no splash, get a 10 in the Olympics. Right? But most people, there's going to be some angle between body and water here. Okay, ultimately, think about this. If we could find the slope here, would that be helpful? If we could find the slope of that curve at that point, that's pretty much exactly what we need, because if we had the slope of that, we could use that to figure out the angle between the line and the x-axis. So ultimately we know the slope here, the slope of this path is dy dx. Well, what do we know about dy dx? It's dy dt, which is 3.6 minus 9.8t over 0.8. dy dt over dx dt. Alright, and so ultimately that would be our derivative here. That would be our slope of our curve at any point. And we want to put what point in there? It's that 1.936 again, because that's our point where that's our time when we hit the water. And so with that we'd have negative 19.21913. And that's where the point if you find the derivative. And we should expect it to be rather steep here because, based on the picture and based on the fact that we only went up 12 and our total distance traveled was like 12.4, so we didn't really travel very far in the horizontal direction, so it should be fairly steep here going in the water. Alright, and then the question is, well, how do we use that information to figure out what the actual angle is then? Okay. Well, let's think about it. If I'm going to draw an exaggerated picture here. Let's say, here's my person going into the water, here's the water. Okay. Ultimately, this would make a right triangle if we drew that down. It's like that. And we want to know theta here. Right. Okay. So the question is, how could we find that angle right there? Well, knowing that this right here, this slope is negative 19, couldn't this be negative 19 and this be 1? Wouldn't that serve the same purpose, no matter how big or small the picture was? That would still represent, and again, that's 19.2 and some change or whatever. I'm just writing 19 for simplicity's sake. But bottom line here is that that y value and that x value would give us a triangle that had exactly that slope for this line, wouldn't it? And if that's the case, then wouldn't the tangent of theta equal negative 19.21913 over 1, or essentially just that? And if I do tangent inverse of both sides, I get 1.519 radians. Alright, and so if you found the actual angle, that was the 9th point. Alright, any questions on parts from number 3?